Imagine standing at the edge of Oblivion. Before you lies the most extreme object in the universe, a black hole. One step forward, and you cross a boundary from which nothing, not even light itself, can return. If you fell into a black hole, you wouldn't just be crushed. You'd be stretched like taffy, frozen in time from an outside observer's perspective, and eventually torn apart atom by atom. But here's the strangest part. You might not even realize you'd crossed the point of no return. Black holes are nature's ultimate paradox, both destroyers and creators, both invisible and detectable, both understood and deeply mysterious. They're places where the laws of physics, as we know them, break down, where time itself can stop, and where the universe hides its deepest secrets. Today we're taking the ultimate journey. We'll approach a black hole, cross its event horizon, and descend into the singularity at its heart. We'll explore what would happen to your body, your perception of time, and your very existence. And we'll confront the most profound questions in physics. What lies at the center? Could you survive? And might black holes be gateways to other universes? This is the complete black hole experience. Let's begin. Despite their name, black holes aren't holes at all. They're the opposite, incredibly dense concentrations of matter packed into impossibly small spaces. To understand what a black hole is, we first need to understand gravity. Every object with mass creates a gravitational field. The more massive an object, the stronger its gravitational pull. Earth's gravity keeps your feet on the ground. The sun's gravity, 28 times stronger, keeps Earth in orbit. But imagine taking all the mass of our sun, about 333,000 times the mass of Earth, and compressing it into a sphere just 3.7 miles across. That's smaller than most cities. The gravitational field of such an object would be so intense that nothing could escape it, not even light. This is a black hole, a region of space-time where gravity has become so strong that it warps the fabric of the universe itself. At its boundary, called the event horizon, the escape velocity, the speed needed to break free, exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses this boundary can ever return. The term black hole was coined by physicist John Wheeler in 1967, but the concept is much older. In 1783, British philosopher John Michell theorized about dark stars so massive that light couldn't escape them. But it wasn't until Albert Einstein published his theory of general relativity in 1915 that we truly understood what black holes were and how they worked. Einstein showed that massive objects don't just pull on things with gravity, they actually bend and warp the fabric of space-time itself. Imagine a heavy bowling ball placed on a stretched rubber sheet. The ball creates a depression, and anything that rolls nearby will curve toward it. Black holes create such extreme warping that space-time essentially folds in on itself. Black holes are born from death, specifically the death of massive stars. Stars are locked in a constant battle between two forces. Nuclear fusion in their cores creates outward pressure, pushing against the inward crush of gravity. For millions or billions of years, these forces balance perfectly, and the star shines steadily. But fusion requires fuel, and eventually even the mightiest stars run out. When a star at least 20 times more massive than our sun exhausts its nuclear fuel, fusion stops and gravity wins. The star's core collapses catastrophically in less than a second. This collapse triggers one of the most violent events in the universe, a supernova explosion. The star's outer layers are blasted into space at 10% the speed of light, briefly outshining entire galaxies. But at the center, the core continues collapsing. If the core's mass is more than about 3 times the mass of our sun, nothing can stop the collapse. Not atomic forces, not nuclear forces, nothing. The core compresses beyond a neutron star into an infinitely dense point called a singularity, surrounded by an event horizon. A black hole is born. The size of the event horizon, called the Schwarzschild radius, depends on the mass. For a black hole with the mass of our sun, the event horizon would be about 1.9 miles across. For one with 10 solar masses, about 19 miles. These are called stellar black holes. But stellar black holes are just the beginning. At the centers of most galaxies, including our own Milky Way, lurk supermassive black holes, monsters millions or even billions of times more massive than our Sun. How these giants formed remains one of astronomy's great mysteries. They may have grown by consuming stars and gas over billions of years, or they may have formed directly from massive gas clouds in the early universe. There's even a theoretical third type: primordial black holes, microscopic black holes that may have formed in the extreme conditions of the Big Bang. If they exist, they could be anywhere, even passing through Earth right now without us noticing. Here's the problem. Black holes are black. They don't emit light. They don't reflect light. By definition, they're invisible. So how do we know they exist? We detect them through their effects on everything around them. Like a detective finding a criminal by the evidence they leave behind, astronomers find black holes by observing what they do to nearby matter. When a black hole shares a binary system with a normal star, it pulls gas from its companion. This gas doesn't fall straight in. It forms a swirling disk called an accretion disk, spiraling toward the event horizon like water circling a drain. As the gas accelerates, friction heats it to millions of degrees, making it glow brilliantly in X-rays. X-ray telescopes can detect these accretion disks, revealing the black hole's location. By measuring the orbital speed of the companion star, astronomers can calculate the black hole's mass. If the invisible object is too massive to be a neutron star, it must be a black hole. In 2019, humanity achieved something remarkable. We took a photograph of a black hole. The Event Horizon Telescope, a global network of radio telescopes working together, captured the first image of M87 star, a supermassive black hole 55 million light-years away in the galaxy Messier 87. The image shows a glowing ring of light surrounding a dark center, the black hole's shadow. The ring is the photon sphere, where light orbits the black hole before either escaping or falling in. The dark center, about 2.5 times larger than the event horizon itself, is the shadow, the region where no light can reach us. In 2022, the same team released an image of our own galaxy's supermassive black hole, Sagittarius A star, lurking at the center of the Milky Way, 27,000 light-years from Earth. Despite being 4 million times the mass of our Sun, it's relatively quiet, consuming matter at a modest rate. These images confirmed what Einstein's equations predicted over a century ago. Black holes are real, and now we're about to fall into one. Not all black holes are created equal, and if you're going to fall into one, your choice matters a lot. Let's say you're in a spacecraft, and through some cosmic misfortune, you're headed toward a black hole. Your first question should be, which kind? If you're approaching a stellar black hole, one just a few times the mass of our Sun, you won't make it to the event horizon alive. The gravitational difference between your head and your feet would be enormous, even when you're still far away. This effect is called tidal force, and it's the same force that causes ocean tides on Earth. But in the intense gravity near a stellar black hole, these tidal forces become deadly. Your feet, being closer to the black hole, would experience significantly stronger gravity than your head. You'd be stretched vertically while being compressed horizontally, like clay being rolled into a long, thin strand. Scientists have a technical term for this: spaghettification, and it's exactly as unpleasant as it sounds. Long before you reach the event horizon, you'd be torn apart into a stream of atoms. For any hope of crossing the event horizon intact, you need a supermassive black hole, 1 million or billions of times more massive than our Sun. The event horizon of such a behemoth would be enormous, possibly millions of miles across. At this scale, the tidal forces at the event horizon itself would be relatively gentle. The gravitational pull on your head and feet would be nearly equal. So let's choose the supermassive black hole at the center of our galaxy, Sagittarius A star, or SGR A star for short. At 4 million solar masses and 27,000 light-years away, it's the closest supermassive black hole to Earth. Its event horizon stretches about 15 million miles across, roughly 16 times the diameter of our Sun. Of course, in reality, you'd never intentionally approach a black hole. But for our journey today, Sagittarius A star is our destination. As your spacecraft approaches Sagittarius A star, the first thing you'd notice is darkness, a perfectly circular void against the starry background of the galactic center. This is the black hole's shadow, the region where no starlight can reach you. But surrounding this darkness, you'd see something spectacular, a glowing ring of light. This is the accretion disk, made of gas, dust, and even torn-apart stars spiraling toward the black hole at tremendous speeds. The inner edge of this disk, heated to millions of degrees by friction, glows brilliant white blue. Further out, cooler regions glow orange and red. The black hole's gravity is so strong that it bends light around it, creating optical illusions. You'd see stars that are actually behind the black hole appearing above and below it, their light bent around the event horizon in graceful arcs. Some stars would appear in multiple locations at once, their light taking different paths around the black hole. This effect, called gravitational lensing, turns the black hole into a cosmic funhouse mirror. The entire view would be distorted, warped by the extreme curvature of spacetime. As you move closer, you'd begin to notice something strange about time itself. A clock on your spacecraft would tick normally from your perspective, but if you compared it to a clock back on Earth, you'd find your clock running slower. This is gravitational time dilation, a direct consequence of Einstein's relativity. The closer you get to the black hole, the slower your time passes relative to the rest of the universe. An hour for you might be 2 hours back on Earth, then 3, then 10. This effect becomes more extreme the closer you approach the event horizon. You'd also feel the ship beginning to accelerate. No longer relying on engines, you're now in free fall, pulled by the black hole's immense gravity. The acceleration would be gentle at first, but steadily increasing. Looking back, you'd see the universe behind you beginning to blue shift, light compressed by your increasing speed. This is the point where most people would fire their engines and escape. The gravitational pull is strong, but you're still outside the event horizon. Escape is possible. Your spacecraft could still break free and return to normal space. But we're not escaping. We're going all the way in. The event horizon looms ahead, an invisible boundary that marks the point of no return. From the outside, it looks like nothing special, just empty space at the edge of the black hole's shadow. But it represents the most fundamental boundary in physics. At the event horizon, the escape velocity equals the speed of light. Inside it, even traveling at light speed wouldn't be enough to escape. Space itself is falling into the black hole faster than you could travel through it. As you approach this boundary, time dilation becomes extreme. For every second that passes on your ship, hours, then days, then years pass in the outside universe. If you could still see Earth, impossibly far away now, you'd watch it age rapidly, seeing the sun rise and set in rapid succession, watching seasons flash by. But Earth couldn't see the same thing happening to you. To any observer watching from a safe distance, your ship would appear to slow down as you approach the event horizon. You'd get closer and closer, but never quite reach it. Your image would freeze, hanging forever at the edge of the black hole, gradually dimming and red-shifting until you faded from view. This creates a strange paradox. From Earth's perspective, you never cross the event horizon. You're frozen at its edge for eternity. But from your perspective, you cross it in a finite amount of time. Both perspectives are correct. They're just describing the same events from different reference frames. This is one of the most profound insights of relativity. There is no universal now. Time is relative, flowing differently for different observers depending on their speed and their position in a gravitational field. Your spacecraft's computer counts down the final seconds to the event horizon. 3, 2, 1. You cross the boundary. Nothing happens. There's no flash of light, no sensation, no marker. The event horizon is just a mathematical surface, not a physical barrier. You wouldn't even know you'd crossed it, except for one thing. When you look back, you can no longer see the universe behind you. The view is cut off as if someone drew a curtain across the cosmos. You've passed the point of no return. Escape is now physically impossible. No matter what you do, no matter how powerful your engines, your future leads in only one direction, toward the singularity at the black hole's center. Welcome to the inside of a black hole. Inside the event horizon, reality becomes strange in ways that are almost impossible to describe. In normal space, you can move forward, backward, left, right, up, or down. You have freedom to move through space. Time, however, only moves in one direction, forward. You can't choose to move backward in time or stop time from flowing. But inside a black hole, these roles reverse. The direction toward the singularity becomes your future, as inevitable and unavoidable as the passage of time itself. You can no more avoid falling toward the singularity than you can avoid aging. It's not a place you're moving toward. It's your future, as certain as tomorrow. Meanwhile, the direction you came from, back toward the event horizon, becomes like the past. You can see it, you can remember it, but you can never go back to it, just as you can never travel back to yesterday. This is what physicists mean when they say space and time swap roles inside a black hole's event horizon. The radial direction, toward or away from the center, becomes time-like, while time itself becomes space-like. It's a complete inversion of everything you've known. From your perspective, the journey continues. You look around the interior of the black hole, and it's empty, just darkness. No walls, no structure, nothing to see except the faint glow of Hawking radiation, theoretical particles created by quantum effects at the event horizon. But this radiation is incredibly faint, barely detectable even with the most sensitive instruments. You check your instruments. Your clock still ticks normally. To you, time passes at the same rate it always has. But if you could somehow compare it to the universe outside, which you can't, you'd find that you're now essentially disconnected from external time. The universe could age billions of years while you experience mere hours. The ship continues to accelerate, pulled inexorably toward the singularity. There's no fighting it, no possibility of escape. You're in free fall, and in free fall you feel no force, just like an astronaut floating in the International Space Station. But unlike the space station, your trajectory leads somewhere no one has ever been and returned from. You've been falling for what feels like minutes, maybe an hour. Your spacecraft is intact and you're still alive. But that's about to change. Even in a supermassive black hole, tidal forces are only gentle at the event horizon. As you fall deeper into the black hole, closer to the singularity, these forces grow stronger, much stronger. Remember, tidal forces arise from the difference in gravitational pull between 2 points. Right now, your feet are closer to the singularity than your head, only by about 6 feet, but that's enough. The gravitational pull on your feet is slightly, measurably stronger than the pull on your head. At first, the difference is subtle. You feel a gentle stretching sensation, like someone pulling on your ankles. It's uncomfortable but not painful. Your body is tall enough that your feet feel more gravity than your head, but the difference is small. But gravity in a black hole grows exponentially as you approach the singularity. With every mile you fall, the tidal forces increase. That gentle pulling becomes stronger. Your spine begins to stretch. Your vertebrae separate slightly. The feeling shifts from uncomfortable to painful. At the same time, you're being compressed horizontally. The gravitational field isn't just pulling you toward the singularity, it's pulling all parts of your body toward the center line of your fall. Your shoulders are squeezed together. Your rib cage compresses. You're being shaped into a long, thin column. This is spaghettification in action. And it gets worse. As you continue falling, the stretching force overwhelms your body's structural integrity. Your bones begin to crack. Your blood vessels tear. Your organs are pulled apart. You're transformed from a three-dimensional human into a one-dimensional string of matter. But here's something remarkable. Even as your body is being destroyed, your consciousness might persist for a few seconds longer. Your brain, compressed and distorted, might still process signals from your dying nervous system. What would you experience in those final moments? Perhaps you'd see strange visual effects as the light around you becomes increasingly warped. Perhaps you'd feel the rush of your molecules streaming toward the singularity. Or perhaps everything would simply fade to black as your neurons cease to function. Eventually, inevitably, your body is completely torn apart. You're no longer a person, no longer even recognizable as organic matter. You've become a stream of atoms, then subatomic particles, falling in a line toward the singularity like beads on a string. This is how black holes consume matter. Not by crushing it into a ball, but by stretching it into an infinitely thin thread and pulling that thread into the center. But the journey isn't over. What remains of you, these fundamental particles that once formed your body, continues falling toward the singularity. And at the singularity, something even stranger awaits. You've been falling for what feels like minutes, maybe an hour. Your spacecraft is intact and you're still alive. But that's about to change. Even in a supermassive black hole, tidal forces are only gentle at the event horizon. As you fall deeper into the black hole, closer to the singularity, these forces grow stronger, much stronger. Remember, tidal forces arise from the difference in gravitational pull between 2 points. Right now, your feet are closer to the singularity than your head, only by about 6 feet, but that's enough. The gravitational pull on your feet is slightly, measurably stronger than the pull on your head. At first, the difference is subtle. You feel a gentle stretching sensation, like someone pulling on your ankles. It's uncomfortable but not painful. Your body is tall enough that your feet feel more gravity than your head, but the difference is small. But gravity in a black hole grows exponentially as you approach the singularity. With every mile you fall, the tidal forces increase. That gentle pulling becomes stronger. Your spine begins to stretch. Your vertebrae separate slightly. The feeling shifts from uncomfortable to painful. At the same time, you're being compressed horizontally. The gravitational field isn't just pulling you toward the singularity, it's pulling all parts of your body toward the center line of your fall. Your shoulders are squeezed together. Your rib cage compresses. You're being shaped into a long, thin column. This is spaghettification in action. And it gets worse. As you continue falling, the stretching force overwhelms your body's structural integrity. Your bones begin to crack. Your blood vessels tear. Your organs are pulled apart. You're transformed from a three-dimensional human into a one-dimensional string of matter. But here's something remarkable. Even as your body's being destroyed, your consciousness might persist for a few seconds longer. Your brain, compressed and distorted, might still process signals from your dying nervous system. What would you experience in those final moments? Perhaps you'd see strange visual effects as the light around you becomes increasingly warped. Perhaps you'd feel the rush of your molecules streaming toward the singularity. Or perhaps everything would simply fade to black as your neurons cease to function. Eventually, inevitably, your body is completely torn apart. You're no longer a person, no longer even recognizable as organic matter. You've become a stream of atoms, then subatomic particles, falling in a line toward the singularity like beads on a string. This is how black holes consume matter, not by crushing it into a ball, but by stretching it into an infinitely thin thread and pulling that thread into the center. But the journey isn't over. What remains of you, these fundamental particles that once formed your body, continues falling toward the singularity. And at the singularity, something even stranger awaits. At the very center of every black hole lies the singularity, a point where all the black hole's mass is concentrated. Here, density becomes infinite, space-time curvature becomes infinite, and our mathematical descriptions of physics break down completely. What is the singularity? Honestly, we don't know. Our equations, Einstein's general relativity, predict that it's a point of infinite density and zero volume. But when equations give you infinities, it usually means the theory is incomplete, that something is missing from our understanding. Think of it this way. General relativity describes gravity beautifully at large scales, and quantum mechanics describes the behavior of particles beautifully at small scales. But these two theories don't play well together. At the singularity, where quantum effects and gravitational effects should both be important, neither theory fully works. We need a theory of quantum gravity, something that unifies these two fundamental descriptions of nature, to truly understand what happens at a black hole's center. Still, we can make educated guesses based on what we do know. One possibility is that the singularity is exactly what the math suggests, a point where matter is compressed to infinite density. In this scenario, everything that falls into the black hole, every atom, every particle, eventually reaches this point and becomes part of it. It's the ultimate recycling, matter stripped down to its most fundamental form and added to an ever-growing point mass. But there are other possibilities. Some theories suggest that quantum effects might prevent the formation of a true singularity, that at extremely small scales, matter might bounce or form some exotic state we haven't yet imagined. In this view, the singularity might be more like an incredibly dense core rather than an infinitely dense point, something like a super compressed ball of matter governed by quantum rules we don't yet understand. Another intriguing idea comes from loop quantum gravity, a candidate theory for quantum gravity. In this framework, space-time itself is quantized, made of discrete building blocks at the smallest scales. According to some versions of loop quantum gravity, instead of ending at a singularity, the interior of a black hole might tunnel through to a white hole in another region of space-time, possibly in another universe. In this model, black holes wouldn't destroy information. They'd pass it through to somewhere else. Then there's the holographic principle, one of the most mind-bending ideas in modern physics. It suggests that all the information about the three-dimensional interior of a black hole is actually encoded on its two-dimensional event horizon, like a hologram. In this view, nothing ever really falls into the black hole in a fundamental sense. Instead, information is smeared across the event horizon. From this perspective, the singularity might be more of a mathematical artifact than a physical reality. The truth is, we simply don't know what happens at the singularity. It remains one of the greatest mysteries in physics, a place where our understanding reaches its limit. What we do know is this: by any classical description, anything that reaches the singularity is destroyed beyond recognition, its information potentially lost forever. But that word potentially is important, because it leads us to one of the deepest paradoxes in theoretical physics. In the 1970s, Stephen Hawking discovered something remarkable. Black holes aren't entirely black. They emit radiation. This discovery was revolutionary because it suggested black holes could evaporate. Here's how it works. Quantum mechanics tells us that empty space isn't truly empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that pop into existence, exist for a tiny fraction of a second, and then annihilate each other. Usually, these quantum fluctuations don't affect anything. But near a black hole's event horizon, something strange can happen. If a particle-antiparticle pair appears right at the edge of the event horizon, one particle might fall into the black hole while its partner escapes. To an outside observer, it looks like the black hole is emitting radiation. This radiation, called Hawking radiation, carries energy away from the black hole. Since energy and mass are equivalent, E equals mc squared, this means the black hole is slowly losing mass. Over an incomprehensibly long time, far longer than the current age of the universe, a black hole could completely evaporate. For stellar mass black holes, this process would take about 10 to the power of 67 years. For supermassive black holes, it could take 10 to the power of 100 years or more. But eventually, the black hole would shrink and shrink until it disappeared in a final burst of radiation. This discovery created a serious problem known as the black hole information paradox. Here's the issue. Quantum mechanics says information cannot be destroyed. If you know the exact state of every particle in a book, in principle, you could reconstruct that book even if it were burned to ash. The information would be encoded in the smoke, the heat, the scattered atoms. It would be scrambled, but not destroyed. But what happens to the information about things that fall into a black hole? If the black hole eventually evaporates into random Hawking radiation, and that radiation carries no information about what fell in, then the information about those things is gone forever. This violates a fundamental principle of quantum mechanics. Stephen Hawking himself struggled with this paradox for decades. In his later years, he proposed a potential solution. Maybe information isn't lost after all. Maybe it's encoded in subtle correlations in the Hawking radiation in ways we don't yet understand. Or maybe it's stored at the event horizon, as the holographic principle suggests. In 2004, Hawking conceded a famous bet with physicist John Preskill, acknowledging that black holes probably don't destroy information after all. But how information escapes from a black hole remains an open question, actively debated by physicists today. This isn't just an abstract puzzle. The resolution to the information paradox will likely require a complete theory of quantum gravity, fundamentally changing our understanding of space-time information, and reality itself. Let's return to our original question. If you fell into a black hole, would there be any way to survive? Based on everything we've discussed, the answer seems to be a definitive no. Tidal forces would tear you apart, the singularity would crush what remains, and even the information about your existence might be scrambled beyond recognition. But physics sometimes offers surprising loopholes. First, there's the question of exactly which black hole you fell into. In a supermassive black hole like Sagittarius A star, you could cross the event horizon intact and survive for minutes or even hours before tidal forces became lethal. In principle, you could experience being inside a black hole, albeit briefly, before meeting your inevitable end. Some physicists have speculated about even more exotic possibilities. What if black holes aren't quite what we think they are? What if the singularity isn't a point of infinite density, but some kind of quantum structure we don't understand? Could that structure be traversable? Then there are rotating black holes. Kerr black holes, named after physicist Roy Kerr, who described them mathematically in 1963. These black holes spin, and their rotation creates a more complex internal structure. Inside a rotating black hole, there's not just one event horizon, but two, and between them is a region called the ergosphere, where space-time itself is dragged along with the black hole's rotation. Some solutions to Einstein's equations suggest that inside a rotating black hole, there might be a way to avoid the singularity. Instead of ending at a point of infinite density, you might pass through to somewhere else, another region of space-time, another universe, a white hole that expels matter instead of consuming it. This is purely theoretical, and most physicists are skeptical. The mathematics allows for these possibilities, but that doesn't mean they exist in nature. The interiors of black holes might be far more chaotic and destructive than these idealized solutions suggest. Trying to traverse a rotating black hole might be like trying to navigate a hurricane in a paper boat. Theoretically possible, but practically impossible. Still, the universe has surprised us before. Until we have a complete theory of quantum gravity and can definitively describe what happens inside a black hole, we can't completely rule out the possibility of survival, or at least the possibility that something of you might persist in some form. This brings us to one of the most tantalizing ideas in theoretical physics: wormholes. A wormhole is a hypothetical tunnel through spacetime, connecting two distant points, or possibly two different universes. Einstein and Nathan Rosen described the basic mathematics of wormholes in 1935, showing that the equations of general relativity allow for bridges in spacetime. Could black holes be one end of a wormhole, with white holes, hypothetical objects that expel matter instead of consuming it, on the other end? The mathematics is enticing, but there are serious problems. First, the wormholes described by Einstein and Rosen aren't traversable. They collapse too quickly for anything to pass through. To keep a wormhole open, you'd need exotic matter with negative energy density, something that probably doesn't exist in the quantities required. Second, even if wormholes exist, the journey through one might be even more violent than falling into a black hole. The tidal forces, the instability of the tunnel, the possible collapse as you pass through, all of these could destroy you long before you reach the other side. Third, there's no evidence that white holes exist. We've never observed anything that looks like a white hole, and it's unclear whether they could form naturally, even if they're mathematically possible. But here's where things get interesting. Some modern theories, particularly those trying to unify quantum mechanics with gravity, suggest that the interiors of black holes might connect to other regions of spacetime in ways we haven't imagined. The holographic principle, for instance, suggests that the three-dimensional interior of a black hole might be fundamentally equivalent to information encoded on its two-dimensional surface. Could falling into a black hole be like passing through a cosmic data processor? Your information scrambled but ultimately preserved. Could you emerge somewhere else, not as yourself, but as information that could theoretically be reconstructed? These ideas push the boundaries of science into speculation, but they remind us that black holes are testing grounds for our deepest theories about reality. They force us to confront questions about the nature of information, the structure of space-time, and the ultimate fate of everything that exists. After everything we've discussed, The journey from the event horizon to the singularity, the paradoxes and possibilities. It's humbling to realize how much we still don't understand about black holes. We don't know what happens at the singularity. We have equations that predict infinite density, but infinities in physics usually signal the breakdown of the theory. A complete description requires quantum gravity, a theory we don't yet have. We don't know if information is truly preserved in black holes, or if it's destroyed despite the principles of quantum mechanics. The information paradox remains unresolved, and its solution will likely revolutionize our understanding of reality. We don't know if black holes connect to other universes, other regions of space-time, or if they're isolated regions from which nothing ever truly returns. The mathematics allows for exotic possibilities, but mathematics and reality don't always align. We don't fully understand how supermassive black holes formed in the early universe. Some galaxies contain black holes billions of times more massive than our sun, existing when the universe was less than 1 billion years old. How did they grow so large so quickly? We have theories, but no definitive answers. We don't know if primordial black holes exist, microscopic black holes formed in the Big Bang that could still be floating through space today. If they do exist, they could make up some or all of the mysterious dark matter that comprises 85% of the matter in the universe. We don't know what happens when two black holes merge. We can detect the gravitational waves they emit, ripples in space-time that travel at the speed of light, but we can't see inside the event horizon during these cosmic collisions. What happens when two singularities combine? Do they simply become one larger singularity, or does something more exotic occur? And perhaps most fundamentally, we don't know if our entire understanding of black holes is correct. General relativity has passed every test we've thrown at it for over a century, but we know it's not the complete picture. When we finally develop a theory of quantum gravity, we might discover that black holes are very different from what we currently believe. Despite all these mysteries, we know that black holes play crucial roles in the universe. The supermassive black holes at the centers of galaxies aren't just passive objects. They're cosmic engines that influence the evolution of their entire galaxies. When matter falls into these black holes, it releases enormous amounts of energy, more energy than nuclear fusion produces in stars. This energy, in the form of powerful jets and radiation, can heat surrounding gas, regulate star formation, and shape the structure of galaxies. There's a remarkable correlation between the mass of a galaxy's central black hole and properties of the galaxy itself. Larger galaxies have more massive black holes, suggesting a deep connection between black hole growth and galaxy formation. We still don't fully understand this relationship, but it's clear that black holes and galaxies evolve together. Black holes also serve as natural laboratories for testing the extremes of physics. Nowhere else in the universe can we study gravity as strong as near a black hole's event horizon. By observing black holes, how they orbit, how they merge, how they affect their surroundings, we test Einstein's general relativity in its most extreme domain. The detection of gravitational waves from merging black holes, first achieved in 2015, opened a new window on the universe. These waves carry information about the collision of black holes billions of light years away, allowing us to study events we could never observe with light. Each detection teaches us something new about how black holes form, how they evolve, and how common they are. And looking to the far future, black holes will be the last objects remaining in the universe. In perhaps 10 to the 100th power years, after all stars have burned out and all matter has decayed, only black holes will remain, slowly evaporating through Hawking radiation. In 10 to the power of 106 years or more, even these will disappear, leaving a dark, empty universe approaching absolute zero temperature. Black holes are not just astrophysical objects. They're glimpses of the universe's ultimate fate. We've taken a journey from the outside of a black hole to its innermost depths. We've explored what would happen to your body, your perception of time, and your very existence. We've confronted paradoxes that challenge our understanding, and that's what makes black holes so profound. They're not just objects in space, they're questions about the nature of existence itself. Black holes force us to confront the limits of knowledge. They show us places where our best theories break down, where our equations give infinities, where our intuitions fail. They remind us that the universe is stranger, deeper, and more mysterious than we can fully comprehend. But they also show us how far we've come. A century ago, black holes were purely theoretical, mathematical curiosities that might not exist. Today, we've photographed them, detected the gravitational waves from their collisions, and mapped their distribution across the cosmos. We've turned the invisible visible and made the incomprehensible somewhat less mysterious. The journey into a black hole is a one-way trip, a descent into darkness from which nothing returns. But the journey to understand black holes, that's an ongoing adventure. With each new observation, each theoretical breakthrough, each gravitational wave we detect, we learn more about these cosmic enigmas. We stand at the edge of understanding, peering into the abyss. And remarkably, from this tiny planet orbiting an average star in an ordinary galaxy, we've figured out that these monsters exist, how they form, and some of what happens inside them. We've taken mathematics and physics and built a map of the unmappable, described the indescribable. That's the real wonder of black holes. Not just what they are, but that we can understand them at all. The universe whispers its secrets to those who listen. Black holes are among its deepest secrets, places where space and time trade roles, where the past becomes unreachable and the future becomes inescapable, where reality itself bends beyond recognition. If you could ask a black hole a question, what would you ask? What lies at your center? Do you destroy information or preserve it? Are you a gateway or a grave? Can anything survive you? We don't have all the answers yet, but we're learning. We're looking deeper, thinking harder, and slowly piecing together the puzzle of what black holes are and what they mean. And who knows? Perhaps someday, centuries or millennia from now, humanity will understand black holes completely. Perhaps we'll solve the information paradox, develop a theory of quantum gravity, and know exactly what happens at the singularity. Perhaps we'll even find a way to harness black holes, using them as energy sources or as portals to distant corners of spacetime. Or perhaps black holes will always remain partially mysterious, always reminding us that the universe is larger and stranger than our minds can fully grasp. Either way, the journey continues. Our journey to understand the cosmos, to map its structures, and comprehend its laws. Black holes are one destination on that journey, perhaps the most extreme destination imaginable. Thank you for joining us on this descent into darkness. The universe is vast, and there's always more to explore. Until next time, keep looking up, keep asking questions, and never stop wondering about the mysteries that lie beyond the stars. This has been Space Echoes,